John Lian. His title is Hunting for Large Complex Structure Limits.
Thank you. I'd like to thank the organizers for the invitation. It's really an honor to be here to pay tribute to Ron on his 60th birthday. So happy birthday, Ron. It seems like there's been a popular practice in this conference to expand on lectures that they have previously gave but had too little time to expand. So I'm going to follow that convention here. So this is basically an expansion of one of the slides in my lecture in the Philadelphia meeting a few months ago. So this is, I'll be reporting on work based largely on a series of joint papers with the following authors: Spencer Block, Antoine, and Srinivas, S.T. Yao, Xiwen Zhu, and on some ongoing work with Ray Fu. So this is basically a revisiting of some old problems that thought about on and off. So let me start by with the following setup. So straight Y will be generically a Calabi-Yau default, always projective. And let script M, Y, be the moduli space of complex structure. Y. And so conventional mirror symmetry tells that there ought to be some kind of partial compactification. Some partial compactification. And some mythical point at infinity called the large complex structural limit. LCS for short, where one can test various statements of mirror symmetry. Like sort of a laundry list. Let me just name a few. One of them is, say, existence of mirror maps from M1 bar to, say, Taylor modulo of mirror. Counting curve. Matching of mixed hot structure from one set of homology group to the mirror one. Odd homology to even homology. So this philosophy has been tested over past, but the approaches in those tests are usually quite ad hoc. They're usually sort of a catch-22 situation. One needs to, well, first find an appropriate choice, and then test whether or not these statements hold true. And they usually involve some guesses of what this singular variety looks like. So what I wanted to do today is to suggest a topological condition that allows one to identify at least candidates for such LCS limit. So to suggest, this is sort of the goal of my talk, a topological condition in some special set. To identify. And at this point, candidates for LCS limit. Candidates because I don't know how to prove that they are in fact LCS limit. So the case study I want to talk about is the following. So I'll start with, I will talk about hypersurfaces. Why? In a fixed, inside a fixed funnel, right? Smooth funnel, right? So the rough idea is to construct a certain explicit D module associated to this setup that translates or that produces the topological condition. X is fixed, so y will vary inside of X.
The D module is over Y?
No, the D module will be over some parameter space. And basically, it will be hyperplane section, the space of hyperplane sections. Okay, so let me sort of give you a flow chart of my talk. So here's what I plan to do. I'm going to start with by sketching the well-known definition of LCS limits. So this notion was made precise by David Morrison and others. And the next stop will be, I will consider the universal family of CY hypersurfaces in X. And I'll use something called the symmetry constraint. Method to produce a D module. So this D module would be something like a what I would call a GKZ-like D module. Sort of in a canonical way. So once I have this D module, I will from that produce a topological condition, and then I'm going to test it on some old and new example. Okay, so that's I will be one. Okay.
Is this D module supposed to be modular in the sense that the ordinal of X is invariant?
Yeah, the D module will encode information about X and symmetry of X, and I'll explain what I mean by capturing. Yeah, so it's basically captured by these two words. Okay, and if time permits, I'll say something about what I had in mind for further tests. of these IDs. Okay, so that's my point. All right, so let me start with LCS limit. Okay, so consider a family of CY of dimension D over the puncture polydisk. So let me, so delta star will be the puncture disk, and this will be an S-dimensional polydisk. So the family of CYs of dimension D, such that I'll assume that the Kadara-Spencer map at each point YB will be my fiber. So the Kadara-Spencer map is assumed to be isomorphic. Next, let Tj be the monodromy operator associated to the J copy of the J factor of the disk. Let me call it along with J disk. And this are assumed to be all unipotent. And let's form the following. Take log of Tj, and where lambda j are some chosen arbitrary positive number. So this is an element of something called the monodromy cone. So from this, one gets canonically a monodromy weight filtration. I'll call it MWF for short. As follows. So this is a filtration, an increasing filtration of length to D. On the middle cohomology of Y, the coefficient Q. And I'll assume that that satisfy the following additional condition. That they're essentially just half of these spaces that are different. Furthermore, we also assume that they satisfy the following non-degeneracy condition. That if I take harm of W2 mod W0 into W0, this would be isomorphic to, well, equal to the Q spec of Nj, where Nj here is just a log of Tj. This condition ensures that this setup produces something called canonical coordinates, but I won't go into the details of that. Okay. So by I can now swing this over to the dual space and produce an equivalent filtration. So this gives rise to an equivalent filtration, but on the dual space, which I'll call S. So basically, S of 2I is simply given by 2D minus 2 minus 2I under the usual parity between homology and cohomology. Okay. So this setup has the following consequences. So first, if you look at S naught, oh, I think I forgot one condition. I require that this be one dimension. So when you swing it around, this also is one dimensional. Moreover, this is invariant under all monodromy. So that if I work over Z, there will be a unique up to sign. Monodromy invariant. Integral generator. Gamma naught in S naught.
Is this wave filtration self-dealing in some sense?
I'm sorry? Yeah, it is in the middle. Yeah, but I like to think about cycle, so I want to keep the two separate. Okay. All right. So let me make one remark. So in the context of SYZ, one expects that this gamma naught should be given by the Lagrangian cycle, Lagrangian torus in one.
Fiber? The
Yeah.
fiber of the SYZ separation, okay.
Yeah, fiber. Okay. All right, next. So I want to talk about, so from this setup, I want to fix a section. Fix a section. Which I'll call omega of Hodge bundle. So this is the fiber of this bundle is just H N0 of YD. So I want to fix a section and define pi to be a local system. Generated by these periods. For some fixed for some fixed base point, B naught. So this is what I refer to as the period sheaf of Y. Which one?
for its cycles.
The cycle, yeah, they all live in rational cohomology. But for the period sheaf, it doesn't really matter because I'm looking at the sheaf of analytic function generated by them. So this is some sheaf of germs of analytic function defined on this puncture coordinates. And because of this, so the existence uniqueness.
N is the dimension is N.
D is my dimension of the fiber Y. Oh, thank you. This is supposed to be, yes.
Is that going to be YB?
Yeah, YD. I mean, I you know, yeah.
B is okay. It's not okay.
You fix some base one. Thank you. Okay, so so this invariant cycle tells us that LCS limit basically says that the space of invariant periods are exactly one-dimensional. In fact, it's generated by exactly this invariant cycle. It's the monodromy invariant cycle. Okay. All right, now I'm going to switch gear a little bit, and I want to consider the following setting. So fix now an n-dimensional Fano variety. It's always smooth. And
Sorry, that's what B is. What is your thought? Phi of B, what is B?
B is D. B is D, and this is the rotation of taking local sections.
this B,
Yes.
B is my, in the previous setup, is the puncture polydisc. So B in the previous setup was this. All right. And I'm going to assume that this variety comes with an algebraic group action, where G is a fixed algebraic group with finitely many orbits. So here I'm going to assume that my anti-canonical sheaf is very empty. Okay, so let V check be this throughout this lecture. This will be L. And in it, let B, so this is straight B, not script B, be the space of smooth hyperplane section. And I want to look at the universal family over B. So D now becomes n minus 1. So the idea is that, well, assume that my moduli space will be some quotient of B. I won't spell out what it is until I get to the test case later. So something I have in mind is something like you take X to be, say, projective homogeneous space, and you take My to be the stable point on the GIT quotient.
Sorry, just to understand, how is the family Y related to the very ample line bundle? Is it the actual section? Is it the actual?
I haven't written down the section in this setup yet, but I will. Yeah. All right, so to answer one question, let me define the following. So let F be a so-called universal section of L. Oops. Given by the following evaluation method. So I take a pair and simply evaluate at a point, at the second slot. So I refer to it as the universal section. And then, so here's a fact. There exists a C cross, well, so there exists a holomorphic N form, omega N, on a certain canonical C cross principal bundle. M over X. Such that omega M over F is a meromorphic, defines meromorphic N form on X with simple pole. along B equals 0. Well, along f of B equals 0. And so this gives me a canonical section.
Is capital omega a chain form or just one form?
Yeah, I'm taking residue. So this reduces by 1. So this is supposed to be an n form. When I take residue, it becomes an n minus 1 form. Okay. So this becomes pointwise. And n minus 1 form on the phi. So when I vary B, I can think of this as a section of this Holmes one. The point here is that here, this formula is supposed to be globally defined on every point in B. B being this. Okay, so the upshot is that I can now lift the period sheaf from the moduli space to this affine variety B. So I can consider the local system of analytic function. Generated by period given by the set. And I'll also call this local system pi. All right, so here's a question. I want to construct an explicit, complete differential system. Say tau for the local system pi. That is, I want tau to have the property that the classical solution is coincide with the local system I started with on B. Check. Okay. the point of this is that I start with a local system, and I'm interested in singular points that don't live in B, but rather in sort of the infinity. That is in the complement of B in this affine space. So the point is to use this differential system, or D module, to somehow extend this local system in some natural way. It's sort of in the sense of perverse sheaf, and use that perverse sheaf to do the detection. Okay, so first, to partially answer this question, let me recall result. So there is a regular polynomial D module on B check such that, so let's call it tau, such that half of this is true. I don't have time to go through the construction, but let me mention that this is well known in a few special cases. So if X is say a smooth toric variety, and if you take G to be the usual dense torus T, then tau is a GKZ system. And if you take X to be a certain wonderful compactification, of a reductive group, then this class of system was studied by Kapernoff. So this gives Kapernoff system. Where the symmetry group, in this case, is G cross G. This space is a certain algebraic compactification of the group G, and it acts on left and right under G. And the third example I want to mention is if you take X to be a projective homogeneous space, then tau can also be written down explicitly. Then tau is generated by, as a cyclic module, the left ideal is generated by vector fields corresponding to G, acting on the linear representation. Together with certain quadratic operator of the form, let me write over here. So together with the theory. with quadratic constant coefficient operator of the form Cg minus lambda acting on the space of second order differential operator, where AI is some linear coordinate. Coordinates on V check. And what is lambda? So lambda here, let me start with Cg. Cg is the second Casimir of the Lie algebra. And lambda is a certain eigenvalue. A certain eigenvalue of Cg.
Sorry, in this case, do we know the family of Calabi-Yau?
Say again?
Do we know the family of Calabi-Yau in this case, or?
Well, no, in what sense? I mean, you can calculate the dimension of B is a certain dimension of the certain irreducible representation. You know the highest weight, so in that sense you know it. If you take special cases like the Grassmannian, you could write down explicit equation for these Calabi-Yau. Yes. Okay, so these are the examples where one can actually write down pretty explicit description of tau. And here, of course, it's well known that these are all given by binomial. Together with vector fields generated by the torus. Okay. All right, next, so I want to give a topological description of the solution of tau. So this is the authors that I mentioned in the beginning in a couple of papers. The first one talking about the special case. I won't go into all the technical detail. I sort of just mentioned the main point of this that I'm going to use. So the main point is that one have a very nice description of the solution of this differential system at any point in V check. So the space of solution is given by the compact supported cohomology in the middle degree over UB, I'll say what UB in a moment, with coefficient in this complex of sheets called SOL. So where UB is the complement of a given fiber, and dxg here is the sheaf of the sheaf of algebraic differential operator on X, twisted by this trivial representation C. And so here is the derived solution sheet. gives you an object in this case. Any questions so far?
Cancel over the mean. I thought
This is well, x on a gx on x through vector field. Yeah, G is the Lie algebra of the group G. So it generates vector field, so it acts on this differential operator. And C here is the trivial module. So this is, I mean, this is just dx mod dxg. Okay, which brings me to the next point. So you have, you certainly have this.
So why be smooth, right?
Yeah. Oh, here y can be anything. So that's sort of part of the point of this formula. That originally, we're trying to understand the sheet for generic B, but this formula allows you to sort of extend it to singular section.
Okay.
Okay, so you certainly have this mapping into the structure sheet. So from here, you get, well, let me just specialize to one case. So if G generates Tx, then Txg is just a structure sheet. In which case, one gets the following description. That the solution sheet is isomorphic to the middle homology of the complement. So this is the case I want to focus on. I mean, there are other cases where G does not generate the tangent bundle, like GKZ, where something, you can say something more. You have to take into account other geoorbits in X in those cases. But let me, for now, focus on this case. So in particular, one gets the following, that you look at the start of my period sheet. This is isomorphic to the solution sheet. If and only if the primitive cohomology in the middle of X is true. So it says that the middle primitive cohomology is the obstruction to tau being the complete system we're looking for. Okay. All right, let me now return to the LCS problem. So what do we want? So we want to look for a certain singular hyperplane section me just call it y infinity. So if this is some point in V check, with the property that the solution sheet at that point is rank 1. So I'm looking for this sort of special rank 1 point. So this is a corollary to the theorem. So in any projective homogeneous G variety, X, they exist an anti-canonical divisor, y infinity, and a monodromy invariant cycle, gamma naught, in a nearby fiber. YB in the family, such that if I look at my period sheaf in the neighborhood, in some neighborhood of B infinity, so this is B infinity, the sheaf is generated by this single period, where U infinity is some neighborhood, some analytic neighborhood of B infinity. So let me sketch a proof. So I'll fix my semi-simple group G, and I'll fix a Borel subgroup. So this construction is going to use something called the Richardson stratification of flag variety, which was studied by many people going back at least 20 years. So B is my Borel, choice of Borel, and I'll write well, B and B plus will mean the same thing. Sorry for the same B. This B has nothing to do with the base space there. So this is the Borel, and I'll write B minus to be the opposite Borel. Then one can define something called open Richardson variety. So for a certain pair, let me denote it by U and W, of element in the vowel groups, one can define the following object. So let's call it X, W, U. This is standard notation in representation theory. So you look at this opposite Borel, mark B, intersect with E plus W, B. So this is called an open Richardson variety in the flag variety, G mod. Do I have 5 minutes?
One of your W's is U, right?
Sorry?
In the definition of open. You wrote W for both of them.
You mean here?
Now in B minus,
One line below.
This is B minus, this is B plus.
what
B would be B plus.
you put W to each cell. B minus WB, B plus WB.
That's right.
Where is
Oh,
B?
sorry. One is U, the other is B. Thank you. As I said, this word certain is loaded here. There's some technical definitions involving something called the P-Bruja intervals, or equivalence classes thereof, which gets rather technical. I won't want to get into that. Suffice to say that I only look at certain special pairs of elements of the vowel group. And the statement is that these guys form a stratification of the flag variety. In fact, under the natural projection from G mod B to G mod P, where P is a parabolic containing B, that the notation is a little bit unfortunate. It's also called pi. So let pi circle U, WU to be the image of X of this Richardson variety. Then the statement is that this gives a decomposition of G mod P. It's a stratification of X called the projected Richardson stratification. So that's step one. Step two. So here's a key observation due to Knudsen and Lamb. So let pi 1 to pi r to be the closure of codimension 1 strata. And look at the union of this codimension 1 strata. And the claim is that this is anti-canonical. Moreover, using representation theory, one can show that the complement of this anti-canonical in X is one dimension. In fact, this is isomorphic to the Hom of between two verbal modules. So these are certain verbal modules. Over G. And by BGG, one knows that this is one dimension. Finally, one has to check that, so together with the result I just stated, this tells us that the dimension of the solution at this point, the infinity, is one dimension. And the last part of the assertion, one has to check that, in fact, that the unique solution up to scalar is of the form integral of an invariant cycle, where gamma naught is the monochromic invariant cycle in nearby phi. Okay. So the upshot is that this particular anti-canonical divisor gives you a candidate for an LCS loop. I'm out of time, but there are some ideas how to test this this hypothesis and see that it produces the correct statement in mirror symmetry. So, thank you.
Is there a nice way to see the equation of this divisor as a vector?
Good question. One can show that this divisor is T invariant. So I was told when I gave a talk elsewhere a few months ago, someone pointed out to me that you can write down an equation using something called the Gelfand-Zeitlin basis.
Oh, okay.
Yeah, so I believe that one can write it down. Oh, yeah. So at least in some example, I know how to write it down explicitly. So take the case of Rachmaninoff. Then this is this equation is given by just the following. So you take the Brugger coordinate, and then just cyclically change the thing. So 2, k 1, and so on, up until n. 1, 2, then k minus n minus k. Sorry. I guess I have to have k minus n. Oops, n minus. So this is the equation.
Okay.
So for G mod P, yeah, I don't know the explicit answer, but presumably one can write it down. Yeah.
There's a mirror symmetry story for homogeneous spaces, and the mirror dual of one is the Lian-Hunting model,
Right.
model on the Lian-Hunting dual group. So I wonder whether that section that we find, actually the complement of it, is the Lian-Hunting model for the mirror dual. Have you checked that? I would expect that.
I don't know. But that,
I mean, it's ongoing work of other people like Reach and
right. It does seem like the Landau-Ginzburg model of the complement does appear quite a bit in this game. But I'm not sure the precise statement to prove.
I mean, Reach has constructed the lambda disgroup model in precisely this space.
For the complement,
Yeah,
I
It
see.
is actually on the complement of that.
yeah,
Or for exactly this anticanonic.
for exactly this reason.
So sounds like this is headed the right direction.
Questions? So you have a space of solutions which can strictly contain periods.
Yes.
Is there some simple interpretation of what are the higher periods?
Yeah, that's a very good question. So in this case, in the case of homogeneous space, the answer is very simple. All the solutions are of this form. So if I want to get the period of the Clavier, I would have to take residue. The point is that you can get all the other solutions by taking cycle in the complement. So in general, there are more of these functions than period of the Clavier because their contribution coming from primitive cohomology. In other words, some of these cycle in the complement are not coming from 2 over cycle of the hypersurface. Yeah.
And that's why it's exactly the primitive cohomology.
Exactly, yeah. That's exactly why that's the obstruction. And so this is for G mod P. And for toric, that's a different story. For toric, it's a little bit more subtle. There, you will have to look at integral over chain rather than just cycle. So these are chain with that bounded on certain divisor at infinity. We also have a precise description of that. So that description also uses the topological description of the solution sheet.
If there are no further questions, let's thank our speakers.